Howdy everyone, I am Mohammad Ahmad Qureshi, working as an assistant professor in Civil Engineering Department at RNG Patel Institute of Technology, Bardoli. In design of structures, we are going through singly RC beam, and in the previous lecture we had studied stress diagram for singly RC beam, neutral axis, equation of neutral axis, moment of resistance, maximum depth of neutral axis, types of beam section, as well as we had solved the examples related to analysis of singly RC beam. Today, we are going to design a singly RC beam. So, in our first example, it is given that design a singly RC beam. We have to design the singly RC beam of rectangular with effective depth equal to twice the width of the beam to resist a factored moment of 120 kilonewton into meter. We have to use Fy 415 Newton per mm square and FCK 20 Newton per mm square. So, first of all, we will write the given data. So, first is given that your depth is equals to twice the width of the beam. Then, factored moment is given as 120 kilonewton into meter, which is approximately equals to 120 into 10 raised to 6 Newton into mm. Then FCK is given as 20 Newton per mm square and value of Fy is 415 Newton per mm square. Here, it is not stated that we have to design a beam using a balanced section, over reinforced section, or under reinforced section. Hence, we will assuming that we are going to design as a balance section. Means we are designing as a balance sections since specification of section is not given in the statement. Hence, for balance section, your mu is equals to limiting moment of resistance, that is mu limit. Hence, for Fe415, value of mu limit will be equals to 0.138 FCK BD square. This equation is given in SP16, page number 10, table C. So, we got the equation as mu limit equals to 0.138 FCK BD square. We already had the value of mu limit as 120 into 10 raised to 6. 0.138 is known, FCK is given as 20, value of B is unknown for us, and the value of D is given in the statement as 2b. So now we will input all these values in this equation. Therefore, 120 into 10 raised to 6 equals to 0.138 into value of FCK is given as 20 into value of B will be as it is B, and D square, and D is given as 2B square. Therefore, after solving this equation, you will get B cube equals to 10.86 into 10 raised to 6. Therefore, value of B will be equals to 221.5 mm. Approximately, we will take this value as 230 mm. Hence, in the given statement, it is given that D equals to 2B. So, after putting the value of B that we obtained earlier in this equation, you will get the value of D as 460 mm. So, value of B is 230 mm and value of D is 460 mm. Now, our next step will be to find the numbers of bars. So, we have to find AST for that. So, using SP16, that is mu by BD square equals to value of mu is given as 120 into 10 raised to 6 upon value of B we obtained in the first step as 230 into value of D as 460 square. So you will get mu by BD square equals to 2.46. Now, using SP16 page 48 or SP16 page 10 table E, you will get the value of PT limit. So for Fy equals to 415 Newton per mm square, you will get the value of PT as 0.823 percentage, and using this particular parameter you will get the limiting value of PT as 0.96%. You can take any of the two values. Both values are near about to each other. Now, therefore, we know the equation AST equals to PT BD by 100. So AST equals to put the value of PT as 0.823 divided by 100 into B as 230 into D as 460. So you will get value of AST as 870.73 mm square. Now, using SP16 page 229, you have to provide the number of bars as well as the dia of the bars. So, from page number 229, you will get near about three numbers of bars of 20 diameter. For this number of bars and dia, you will get AST as 942 square, which is greater than 870.73 square. Hence, these bars are okay. We may provide three numbers of 20 dia bars. Now, we know that value of effective cover is 40 So, we had the value small d equals to 460 which is calculated earlier, and effective cover as 40 So your overall depth capital D equals to small d plus e, so 460 plus 40, which is equals to 500 Hence your overall depth is 500 Alternatively, you may also calculate this value of PT by using the equation PT equals to 50 FCK by Fy 1 minus under root of 1 minus 4.6 mu upon FCK BD square. So, after putting the value of FCK as 20, Fy as 415, Mu as 120 into 10 raised to 6, FCK 20, B 230, and D 460, you will get the value of PT as 0.824%, which is almost near to 0.823% that we had obtained from SP16 page number 48. Either you may use this terminology or you may go through this formula. And after achieving the value of PT as 0.824%, you have to go through this equation, that is AST equals to PTBD by 100, and then you will get the AST near about to 870 only. Then by considering the bars and the number of bars, you may get the value of three numbers 20 dia bars. This is an alternatively method. You may go through this method also. So this is the design of singly RC beam. Hence we had provided three numbers of 20 dia bars over here. By this way, you have to design a singly RC beam. We will go for next example. In this example, it is given that design a rectangular RC beam simply supported over an effective span of 4 meter. Effective span is given as 4 meter. Loaded with a service load of 25 kilonewton per meter, including self weight. Suppose this is your simply supported beam whose span is given as 4 meter and it is loaded with service load of 25 kilonewton per meter. including its self weight. Then take partial safety factor 1.5 for load and width of the beam is 250 mm. Use Fe415 and M20 grade of concrete. Here width of the beam is given, means here B is given as 250 mm, but the depth is not provided. Hence we have to calculate first the depth of the beam. So here firstly we will go for factored load. So the factored load will be equals to 25 into 1.5. So your factor load will be equals to 37.5 kilonewton per meter. That is, your W is 37.5 kilonewton per meter. We can easily calculate the moment, as we know that mu equals to WL square by 8. So here your total factored load is 37.5 kilonewton per meter. Hence your mu equals to W. W is nothing but 37.5 into L. L is given as 4 meter effective span, hence 4 square divided by 8. So you will get the value of mu as 75 kilonewton into meter. So this is the value of mu. In this example also, it is not given whether it is an balance section, limiting section, or over enforced section or under enforced section. Hence, I am assuming that we are going to design as a balance section. Balance section is also known as limiting section. Hence, for Fe415, we know that mu limit will be equals to 0.138 FCK BD square. This equation is given in SP16, page number 10, table number C. So after putting all these values, 75 into, it is in kilonewton into meter, and we have to input the values in terms of newton and meter. So 75 into 10 raised to 6 equals to 0.138 into value of FCK is 20 into value of B is given as 250 mm. So your B will be 250 into D square as it is. Therefore, after solving this equation, you will get D square equals to 108695.65. Therefore, your D will be 329.70 mm, approximately 330 mm. So here your small d is 330 mm. Now, as the dimensions of the beam are calculated by us, that is B equals to 250 mm given in the data and D equals to 330 mm we had calculated over here. Now we will go for AST. So we have to find the value of AST. Now, we know that mu by BD square equals to value of mu is 75 into 10 raised to 6 upon value of B is 250 and value of D we had calculated earlier as 330. So mu by BD square equals to 2.76. Now, as we had calculated earlier the value of PT by using SP16 page 48 table 2 or from SP16 page 10 table E limiting PT, we may calculate by any of the two methods. So now from SP16 page 48 table number 2, value of Fy is given as 415 Newton per mm square. Hence, you will get the value of PT as 0.955%. Or you may calculate the value of PT by using the equation PT equals to 50 FCK by Fy 1 minus under root of 1 minus 4.6 mu upon FCK BD square. By using this equation, you will get the value of PT as 0.952%, which is almost near to 0.955%. Hence, we will go for AST as we know that AST is equals to PT BD by 100. So value of PT as 0.955 upon 100 into B 250 into D 330. So you will get the value of AST as 788 mm square. Now from SP16 page 229 we have to provide the number of bars. So 4 numbers of 16 dia bars we have to provide, and for that your AST will be equals to 804 mm square, which is greater than 788 mm square. Hence we can provide 4 numbers of 16 dia bars. Or you may consider, this is the another method, you have to consider dia of the bars. Here I am considering 16 dia. So your small AST will be equals to pi by 4 into 16 square, which is equals to 201.06 mm square, and then we have to find the number of bars. So number of bars equals to nothing, capital AST upon small ast. Here value of capital AST is 788 and value of small ast is 201.06. Hence your number of bars will be approximately 3.90 numbers, which will be equals to 4 numbers. Hence your AST provided will be equals to 4 into 201.06 equals to 804.24 mm square. This value is almost equals to this value. I would prefer that you will go for SP16 page number 229 only, as this method will be less time consuming. You may easily get the numbers as well as the dia of the bars. And here we are considering the cover as 50 mm. So small d we had obtained as 330 mm. So your capital D will be equals to small d plus effective cover. So 330 plus 50. So total overall depth is 380 mm. And here we had provided four numbers of 16 dia bars. So these are 1, 2, 3, 4 numbers of 16 dia bars. Now we will go for next example. In the next example, it is given that a RCC beam section of size 300 mm into 500 mm is subjected to a design moment of 120 kilonewton into meter. Here it is given as design moment, and in the first example it is given that a factored moment. In the first example, it is given as factored moment, and here it is given as design moment. Full stop. Find the area of tension reinforcement required, means we have to find the value of AST, area of tension reinforcement. Also calculate the minimum and maximum area of tension reinforcement. We have to calculate the minimum area of tension reinforcement. Minimum area of tension reinforcement is given in IS code, as well as the maximum area of tension reinforcement equation is also given in IS code. And use FE415 M20 and the effective cover is 50 mm. So here the size of the beam is given as B equals to 300 mm and capital D equals to 500 mm. Effective is not given. So we have to assume that this 500 mm is given as overall depth, that is capital D. So here this will be your AST and this will be your small d, that is effective depth, and this will be your effective cover. So effective cover is given as 50 mm. So small d will be equals to capital D minus small e. So you will get the value of small d as 450 mm. And the value of mu design moment is given as 120 kilonewton into meter, which will be equals to 120 into 10 raised to 6 Newton into mm. So now we have to firstly calculate the area of tension reinforcement, that is AST. And as we know that we can calculate AST after achieving the value of PT. So first of all, we will go for the equation mu by BD square. So value of mu is given as 120 into 10 raised to 6 upon value of B is 300 and value of small d is 450 square. So we will get mu by bd square equals to 1.975. So for Fe 415 using SP16 page 48 table number 2 or SP16 page 10 table E, or by using the equation Pt equals to 50 Fck by Fy bracket 1 minus under root of 1 minus 4.6 mu upon Fck Bd square. You have three options for finding the value of Pt. So for Fe415, and we are using SP16 page 48 table 2. So you will get the value of PT as 0.630%. Now, as we know that capital AST equals to PT BD by 100. So after putting the value of PT as 0.630 and value of B as 300 and value of D as 450, you will get the value of AST as 850.5 mm square. And after using SP16 page number 229, you have to provide three numbers of 20 dia bars having total AST as 942 mm square, which is greater than 850.5 mm square. Now, also we have to calculate the minimum area of tension reinforcement, and as we know that minimum area of tension reinforcement or minimum area of reinforcement equation is given in IS 456 2000 page number 47 as AST by BD equals to 0.85 upon Fy. So capital AST equals to 0.85 into, after cross multiplication, value of B is given as 300 and value of D is 450 upon characteristic strength of steel Fy is given as 415. So you will get capital AST equals to 276.50 mm square. Then our next step will be maximum area of reinforcement. In IS code number 456 2000, page number 47, one equation is given as AST equals to 0.04 B into capital D. So 0.04 into value of B is given as 300 and the overall depth is 500. So you will get the value of capital AST as 6000 mm square. So here capital D 500, small b 300, small d 450 mm, and E equals to 50 mm, and the area of steel is three numbers of 20 dia bars. So, by using these two equations that are given in IS code, we had calculated the minimum reinforcement and maximum reinforcement. Now, we will go for another example. Design a singly reinforced rectangular beam for factored moment. Here the moment is given as 160 kilonewton into meter, and we have to find the area of tension reinforcement required. The width to effective depth ratio for the beam is 0.7, means here it is given that the width to effective depth, that is small d, is equals to 0.7. Hence we may say that your small b is equals to 0.7 d. Value of b and d both are unknown for us in this example. So either we have to calculate the value of b, or we have to calculate the value of d first, so we may get the remaining value. So, and the second data is given as mu equals to 160 kilonewton into meter. So have to design as balance section, and we know that for FE 415 value of mu limit is equals to 0.138 FCK BD square. This equation is given in SP16 page 10 table C. While practicing at home, you have to write this concept nearby to the equation. So you will remember these values, that on this page number and in this table this equation is given. So here value of mu limit is given as 160 into 10 raised to 6 for Newton into mm conversion, 0.138 into value of FCK is given as 20 into B is nothing but 0.7D into D square. So after solving the above equation, you will get the value of D cube as 82.81 into 10 raised to 6. Therefore, small d equals to 435.88 mm, approximately 440 mm. Hence, after providing small d equals to 440 mm in this equation, you will get b equals to 0.7 into 440 equals to 308 mm. So here dimensions are calculated by us as b equals to 308 mm and small d equals to 440 mm. Since the effective cover is given as 50 mm Therefore, capital D equals to small d plus effective cover. So you will get small d 440 plus E as 50, approximately capital D equals to 490 mm. Now we have to calculate the value of AST, as it is given that find the area of tension reinforcement required. Hence, we know that to find AST, we have to use SP16, and from SP16, using the equation mu by bd square, and value of mu is given as 160 into 10 raised to 6 upon value of b that we had calculated earlier as 308, and value of small d as 440 square. So you will get value of mu as 2.7. Now from SP16, page number 48, table number 2, or SP16, page number 10, table number E, you get the value of PT limit as 0.96%, or by using the equation PT equals to 50 into FCK by Fy into 1 minus under root of 1 minus 4.6 mu upon FCK BD square. So I will prefer this. So you will get for Fy equals to 415 Newton per mm square, you will get the value of PT as 0.928%. And as we know that capital AST equals to PT BD by 100. So value of PT as 0.928 into value of B as 308 into value of D as 440 upon 100. You will get capital AST as 1257.6 mm square. So from SP16, page number 229, you will get four numbers of 20 dia bars having AST as 1256 mm square, which is greater than or equals to 1257.6 mm square. Hence, here your capital D overall depth, your B 308 and small d 440, and value of E. Here there is a mistake. Here the small e is 50 mm, and here the capital D we had calculated here is 490 mm. Hence, 4 bars of 20 dia are provided here, and this is the cross section of the beam. So by this way, you have to design the singly reinforced beam for the factored moment, or by simply finding the overall area of the beam, and finally by providing the area of steel in the given example. So we will just go for the revision regarding all the examples. So in the first example, it is given that the effective depth is equals to the width of the beam. So here we are simply taking D equals to 2B. Then the factored moment is given as 120 kilonewton into meter. So we are just converting this kilonewton into meter into newton into mm. And after that, we had designed a balance section, and as we know that for balance section, mu equals to mu limit, and using SP16 page 10 table C, and for Fe415 grade of steel, we get the value of mu limit as 0.138 FCK square. And after plotting all these values in this equation, you will get the value of B as 230 mm, and then putting this value in the equation D equals to 2B, you will get small d equals to 460 mm. And our next step is to find the area of steel, as we have to provide the steel for the particular beam. Hence for that, we have to use the SP16 code, and from SP16 one formula is given, that mu by bd square. So after inputting all the values of mu, b and d, you will get one value as 2.46, and you may use SP16 page number 48 or SP16 page 10 table E, or PT equals to 50 FCK by Fy into 1 minus under root of 1 minus 4.6 mu upon FCK BD square. All these three values will be almost near to each other. So you may take any of the three values. Hence, after calculating the value of PT, you have to use the equation AST equals to PD BD by 100. And then you have to provide the number of bars as well as the dia of the bars using SP16 page number 229. And then lastly, you have to draw the cross section of the beam showing the overall depth as well as the width of the beam, depth of the beam, and effective cover within the reinforcement details. In the second example also, almost all the procedure is same that we had discussed in the first example. And in the second example, we had designed a balance section. In the third example also, same procedure. Then we have to find the area of tension reinforcement, and we had calculate the minimum and maximum area of tension reinforcement as per IS code. Both these values are given in IS 456 2000 page number 47. And in the last example, the width to effective depth ratio for the beam is 0.7, and we have to find the area of tension reinforcement, that is AST, and then lastly we have to provide the number of bars required for a particular singly reinforced rectangular beam for the factored moment 160 kilonewton into meter. In the next lecture, we will go for some more examples related to design of singly reinforced beam. Thank you.